Okay, line P5, learning task 2, we're going to be taking a look at high voltage transformer connections. And because we are looking at high voltage connections, we're going to actually have to cover a fair bit of high voltage theory just before we can even get into what the actual connections themselves are. So, before we even get to figure number 1, let's start with a little diagram of my own over here. We're going to go and start with a cross-section of a high voltage cable. And what a high voltage cable is going to do is it's going to go and have a conductor that is going to go and be in the center of that. Inside the very center, we have the conductor. Around the conductor, we are going to go and have a thin shield that's going to go around here. And it's going to be made up of generally plastics that are going to be impregnated with small amounts of metallics to make them conductive. You've probably seen this before when you're stripping out tech cables, that right between the actual thick insulation that goes around the conductor, there's going to be this kind of papery black, like another layer of stuff that's going to be around there. That acts the same as this. This is going to be referred to as being my strand shield. And the strand shield is going to go and help us to go and even out a bunch of electrical flux lines. We're going to go and talk about that a little bit later on. Then around the outside of the strand shield, because everything so far is conductive, we are then going to go and place a much thicker chunk of what we would normally call insulation, but in this case we are going to go and call this thing the dielectric over here. The dielectric is going to go and be my insulating device, but it's going to be an insulating device that is going to be underneath electrical strain. And if you go back to second year once again, take a look at everything that you learned about capacitors, you found that a capacitor is going to be two charged objects, differing polarity, that are then going to go and have some insulation in between. That insulation is going to go and have its orbitals distorted, right? If we distort an orbital far enough, we'll break the electron bond, and at that point we end up with current flow. They refer to anything that's to do with insulation, they refer to this as being, once again, just our dielectric on our high voltage cable. And then around the very outside of that, we're going to go and have one more layer that is then going to go and be a grounded, it can be plastic, but it's going to be impregnated with metal, but it's going to be a grounded structure that is going to go around the outside. And then we are going to go and refer to that as being another shield, or my ground that goes around the outside. And this one is known as my insulation shields. Insulation shield that we're going to go and have around the outside. And what happens is that because we have got high values of voltage on our actual conductor that's going to be at the very core of this over here, it is going to go and create a bunch of electrical flux lines. We're not talking magnetic flux, we're talking electrical flux lines, and those electrical flux lines are going to go and look for a path, or they're going to go and look for something that they can go and, oh, I just erased the wrong thing inside there, some way for them to go and even their way out. And so what those electrical flux lines will do is they're going to go across to our nearest grounded object. Now, if I didn't have this guy on the outside, my insulation shield, and if I place this thing over top of Earth, we'll just place this over top of Earth, what would happen is that all of those high voltage flux lines that would be inside of here would then go and try to shoot across to Earth, because that for them is going to be, you know, the path that they're looking for. They're always trying to go from a high to a low. And so what we see is we would see that down here in this lower section of the cable cross section, that we'd have a lot of electrical stress, but up here in the upper section, we've got next to no electrical stress. Well, if you stress anything great enough, it's going to go and lead to a failure. So we want to go and even out this, and the way we even this out is, let me just erase these lines here, is we go and place that insulation shield around the outside, and this insulation shield gets attached, grounded down at the end. And what that does, in effect, is it allows all of this electrical flux, rather than going directly across just to the ground on the bottom, now because we have distributed through that electrical connection, because we have now distributed ground basically all the way around, it evens out the amount of stress inside of our cable. And that's what we're going to be doing in a lot of the connections that are coming up, is we're going to be looking to go and prevent point loading of our insulation, which is going to lead to failure. We want to go and even out the amount of electrical stress around it. Okay, let's talk about the actual connections. The connections themselves are going to be done through what we refer to as bushings. And bushings are going to come in all sorts of different shapes and sizes depending upon the amount of voltage and the area that we are going to be making a termination. All of them are ultimately going to go and have a couple of things in common. First of all, they are going to go and have a conductor. I'm just going to draw it on the biggest one. A conductor that is going to go all the way through the center and is going to go and leave us with a connection point on the outside, or at the other end. The second thing that they're all going to go and have in common is that they are all going to be made up of insulating type of material. And that insulating type of material is going to go and surround that conductor that we had in the very center. And that insulating material is also going to be surrounding the area where this thing would go and bolt into a can, any sort of a enclosure. So that the insulation is both going to be above on the outside of the can as well as below on the inside of the can over here. The second thing that we're going to go and see off of the, or I should say the third thing that we're going to see is we're going to go and see an increase in length dependent upon the value of voltage. I can very confidently tell you that right now this one is designed for the lowest value of voltage. This one over here is designed for the highest value of voltage. And I know that off of the fact that my length is increasing as I'm going up off of these, as well as I'm starting to go and get a bunch of skirting. And the skirting does a couple of things for us. First of all, electricity is going to want to travel on the surface. It's not going to want to travel to the center because these things are going to be made up of ceramics or polymers, which are not going to go and conduct electricity. You know, it's far easier for us to go and track electricity across the surface. So as soon as we do this skirting, what in essence has happened is we now have a path that is getting way longer because it's a zigzaggy path. If I'm going to go all the way over from the top of my bushing to the conductor on the inside, so if this was where the top was, I would have to go and travel over top of that. And if I would stretch that squiggly line out, you'd see that it's, very, very long. In essence, we could do the same thing as what we see here on this bushing with a straight tubular one, but that straight tubular one would have to be way, way taller. And the taller it is, the more unstable it's going to be, the more, mechanical bracing you're going to have to put onto it, etc., and the easier it's going to be to break off. So it's easier to keep these things a little bit shorter, a little bit more squat in their profile, but then to go and place all of that skirting on there. The skirting also does a couple of other things. If it's going to be raining outside, that skirting is going to go and allow water to go and cascade over from one to the other, so it's not going to flow onto the insides like that. The skirting is also going to go and prevent dust and contaminants. So if I got a lot of dust, the dust is going to sit over there, the dust is going to go and sit over there. Maybe we should pick a different color dust. Let's go with some red dust here. It's going to sit on those edges, but it's not going to go on the inside. And once again, the dust is going to be something that we're going to be able to go and track through. We don't want to go and have any sort of a tracking surface on high voltage because then we have danger of flashover, which is where we're going to have an arc that is going to go and strike, and it's going to go all the way across from here over to, remember, we're going to be mounting these inside of a grounded can. It would be an arc that would go all the way across from our line down to our grounded can. We just do that through length, skirting, and keeping then all of our insulation clean afterwards. When it comes to actually terminating the cables, now we're going to go take another look at one of those cables. We looked at the cross section at the very, very beginning over here. We said that in the cross section, we got the conductor inside there, we got the strand shield, then we got the insulation, or what we're going to call the dielectric, and then around that we've got the insulation shield, which is going to be grounded. Now we took a cross section of the cable over here. Now we're going to go and take another cross section, but now we're looking into it sideways. I'm going to split this thing into two halves. This is going to go and be my normal side over here, my cable. And what we see is we've got that insulation shield, which we already described, going around the outside of our cable, which is going to go and even out all of those lines of flux that we see on the inside. This is going to be my electrical flux lines inside of here. But then what happens is when we go and cross over onto this side over here, this is where my termination end is going to go and be. And on my termination end, we've got our high voltage conductor that's going to be inside the very middle. That high voltage conductor is then going to go and have its strand shield that goes around the outside, which just acts as an extension of it, prevents some corona and stuff like that you're going to hear about inside of 4.3. By the way, corona on high voltage, it's not a virus, it's ionized gas that is highly destructive to components. We see that we've got this conductor that's going through the inside, and then we see that on the outside of this, that we have got this insulation shield. And because I've got that insulation shield that stops over there, when it comes to my termination, I'm going to have to do a bunch of stripping of my cable. I'm going to go and strip back the insulation so I can access the actual conductor. Then I'm going to go and strip back the outside part of the insulation, which is going to be that insulation shield. But as I strip it back, we are going to go and still have lines of electrical flux that are going to be emanating from here, and they're always going to be looking for a point of lesser potential. And so they're going to go and shoot over to there because that's the nearest grounded section. What we start to see is we start to see an area of our insulation that is going to be really, really, really dense with electrical flux. And because it gets so dense with electrical flux, that means we're going to be distorting the orbitals on the actual atoms again, and if we have enough stress inside of there, we're actually going to break them down and go into conduction. This would be bad, obviously. You don't want your insulation to start conducting. It's going to go and lead to carbon pitting, areas where we're going to go and get gases and corona and stuff inside there. A couple of different terms for what we have inside of here as well. We are going to go and have a couple of distances that are going to be labeled over here. Depending upon the value of the voltage that we are trying to insulate against, we are going to go and have what's called creepage distance. And creepage distance is just how far voltage can track along a surface back. So this length over here is going to be my creepage distance. Obviously, the higher value of voltage, the more creepage distance that I'm going to go and need to have across there. The other thing that we are going to go and have is we're going to have another term called stress relief. We need to go and take care of all of this electrical stress that's happening right over there. A couple of ways that we used to be able to go and do this. One of the ways we used to do this is we used to build up a cone out of something that was called pennant tape. And pennant tape was just going to be a type of actual tape that had some conductive properties inside of it. And we would go and wrap, layers of stranding and all sorts of stuff into there. It was a technical sort of thing to go and do. But basically, we would take this tape and we would increase the outside of this. We would basically wrap tape around the actual conductor. I'm just going to draw tape here as being green, so we just wrap as a cone, sort of like that. Wrap as a cone. And then across the outside of that, we would then go and place this other dark green thing, which would be an increase in my insulation. And then we would go and wrap a bit more tape over top of that whole thing. And what that would do is that would distribute these electrical lines of flux. The electrical lines of flux don't like to go together because they want to repel anything that's similar. So those electrical lines of flux, instead of all going to here, would now start to go along here. It's a bit further distance, but they don't have to be as close to those other lines of flux anymore. And so what we're able to do is we're able to go and even up the amount of stress that we'd have across there. This used to be done through pennant tapes, and you had to be careful in how you did it, and it was a specialized type of field. These days, we have gone to doing the same thing as the pennant tapes, but we're going to do it through pre-made ends. One of those ends is going to be the geometric stress relief, or the stress cone over here, which is going to be composed of this section up top over here. It's just going to slide over top of our conductor. This section is going to be insulating type of material, dielectric, and then it is also going to go and have what I'm highlighting over here in green, which is going to go and be my outside component over here, what we refer to as the insulation shield or sometimes the semicon. That is going to be part of it as well. So to do a termination with this, I'm going to go and strip back the outside here for my creepage distance. Once I have my creepage distance stripped back, then I'm going to go and slide this assembly onto there. And this assembly is going to have to make contact with my semiconductor or my insulation shield down here. Once again, does the exact same thing as the pennant tapes. Because those lines of flux don't want to be close to each other, they're going to go and spread out across here because they can all get to a little bit of grounded area. The other way that we're able to go and do this is through something called capacitive stress relief. And capacitive stress relief is going to go and bring all of our electrical lines of flux back to the same point, right over here, but it is going to go and take them through an easier path. And we've got to go and deal with the term permittivity. Permittivity is going to be the ability to carry electric flux. Okay, we've had permeability, which is the ability to carry magnetic flux. Now we have permittivity, which is the ability to carry electrical flux. all we're ever looking for is, the path of least resistance, whether that's going to be for magnetic flux, electric current, your amount of workload. Everything everywhere looks for the least amount of work. And so what I have is I have got my regular cable dielectric, my insulation, that's going to be all of this over here. And it's going to be hard for those for those electrical lines of flux to set up inside it. So what I'm going to do is I'm going to slip on another little tube that goes around the outside. And this is going to be what we refer to as a high K, or a high permittivity type of tube. What it's going to do is it's going to go and take my electrical lines of flux. My electrical lines of flux have the option that they could either try to travel from here all the way back through my regular cable insulation, my regular dielectric, which has got a relatively low K. That looks like a lot of work. Or they could just go and shortcut through my regular cable insulation directly across to this tube and then take that easy path all the way back over here. And at that point, we see that all of my flux lines would be combined inside of this tube, but this tube is able to go and withstand it. It's the other way that we can go and distribute our lines of electrical flux. It doesn't matter what you are doing, whether you're going to be using geometric stress relief, whether you're going to be using high K stress relief, or whether you're going to be wrapping that cone all the way around. All that we're ever trying to do is distribute those lines of flux across there. We've got a couple of different classes of terminations as well. IEEE is going to go and define 3 classes, and our high voltage is going to be assessed according to IEEE. Class 1, 2, and 3, we really only go and use 2 of these. We're going to go and use the class 3, which is going to give us stress relief only, and that's going to be things like this, that we're going to use indoors or inside of, transformers that have got a rain shield or things like that. Our next termination is going to go and be class 2. It's going to be stress relief and anti-tracking, so it's going to go and have a bunch of skirting off of it, generally speaking, preventing it from going across, from one to the other. They say the most common ones are going to be silicon and porcelain. You're going to see silicon, porcelain, and glass that are going to be used for all of these because they are vitreous or glass-like on the surface. You know how easy it is to go and clean off glass because it's so shiny. Therefore, a lot of stuff doesn't stick to it. You don't want to have anything that's going to be, a really porous type of substance because you're going to build up contaminants and not be able to get rid of them. Class 1, stress relief, is going to go and be stress relief, so it's going to go and distribute those electrical lines of flux. Anti-tracking, so we can't have as much surface creepage that's going to go and happen across it, and then sealing against the environment. So it's actually going to go and usually use some sort of impregnation or epoxy or something like that that's going to prevent us from actually having air pockets or moisture pockets inside there, particularly in areas where we have rain fog. So this would be stuff like outdoors. They're usually going to have skirted silicone or porcelain. Silicone is able to be molded so that it's going to be highly glossy as well, lower amount of contaminants that we're going to be able to go and pick up. And sometimes we'll have combinations between the 2 of these. That skirting is going to go and do a couple of things. Once again, it is going to go and increase the amount of creepage distance that we're going to go and have, and at sometimes we're actually going to go and have differing sizes of skirting that are going to happen. This 3rd ring down is going to be larger, and then the 2nd ring down is going to be 3rd larger, whatever it's going to be. And sometimes when we see those larger values, it's so that anytime that we have got rain that's going to be falling, that rain cap, it's going to flow down, the water's going to fall, and if I just have a straight side, I could go drip, 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 drip over here, and I could eventually create a path all the way down. What this is going to do by having a couple that are going to be larger, smaller, is it's going to fall far enough here that it's going to start to break up the water, so we have less chance of this actually forming, a path that's going to go all the way across here. The other insulation termination that you should be familiar with, the code actually reference it, is going to be the pothead termination. All right, I'll give you a second to snicker, and then we'll move on past this one. The pothead was used where we had cables that would oftentimes have multiple conductors on the inside, and we needed to go and seal them. It was going to be a class 1 termination. Stress relief, anti-tracking, and sealing against the environment. And what we would do inside of here is I've got a cable. This cable is going to go and have 3 conductors that are going to be inside of it. Insulated conductors, red, black, and we will go with our blue conductor. they're going to be carried up to the very bottom of these bushings. These bushings are then going to go and carry the conductors the rest of the way through. Now inside of here, what we will do is we are going to go and build up pennant tapes. So coming off of here, there would be a buildup of a whole pile of pennant tapes. So we'll just make this the pennant tape that we're going to place around here. We'd insulate around each of these. Once we had the pennant tapes all the way around, then we would go and put this cap on, the terminations that would go on, and then we would go and pour into here liquid pitch. It's going to be an oily, it's like tar that would go over top of everything, and it would just fill the entire thing over here. And then that's going to go and harden up, and we would have an oily, so it's going to be non-conductive, type of termination side here. Because it is oily as well, it's also going to go and shed water. If there was any water that did manage to get into the pothead, which is usually going to be like a large, kind of like a pewtery type of metal, aluminum, that we would have off of there, if anything does get on the inside, then it would not be able to get all the way through. We did use it a lot more with an old type of cable called PILC, paper insulated lead cable. This PILC cable is obviously going to be much less common. Lead was great because you can bury it underground. It doesn't go and, break down very quickly. It's relatively soft, but it is heavy and it's lead, so it's going to be relatively toxic. People don't like to go and work with it. We can use these on other types of cables, but it's less commonly used on other types of cables. The other thing is, any of these, if you run into them in the field and you get asked to go and take these apart, be aware that a lot of the times the pitch or the tar that was going to be inside of there was going to be treated with, wait for it, PCBs, because we have got something that burns, pitch or tar, but we don't want it to burn, so we want to go and add some chemicals to the inside of it. If you ever start your own company and you're starting to look at taking on some high voltage jobs, be very careful, because in some cases, what you assume you're going to make off of the job, you could go and lose easily when it comes to disposal of old components, because it costs you a lot of money to go and get rid of stuff. You're not allowed to just like turf it into the bed or something like that. You need to go and get rid of this stuff properly as part of your contract, and you're just going to be written in there, proper disposal, etc. And if you don't read that part and don't figure out what your disposal costs are going to be for a transformer filled with PCB oil, or for some of these pot heads, things like that, if there's asbestos involved, it can really add up very, very quickly. All right, we're going to go through the steps on making a connection. They just go through here, stress cone termination. This is going to be for a 15 kV one, so we are going to go and read from inside of our manufacturer's documentation. You never do one of these without fully reading the documentation first, because these things are going to be very expensive table terminations, and secondly, the cables themselves are very expensive. If you screw it up, you can't afford to just cut back another meter of cable in a lot of cases. So you're going to read everything real careful, and then you're going to follow those instructions. If we've got a 15 kV cable, we would go and have to use this dimension. Dimension A is going to be what we would strip back our cable. So we see that A is going to be the distance between that insulation shield and between the conductor itself. So I'm going to start by stripping back insulation shield. I'm going to have the depth of my terminal lug barrel. So let's say that I've got a 2-inch barrel over here. That would mean that I'm going to start by taking from the end of my cable, I'm going to take a total of 15 inches plus this 2. So I would strip back a total of 17 inches all the way from here to here. Once I get, oops, sorry, not from there to there, but from here to here. So I'm going to strip back 17 inches of cable. Once I get the 17 inches of cable stripped back, I'm then going to go and strip back the actual insulation 2 inches, and then I'm going to go and tape over the ends so that I don't accidentally bend these out or flare them or anything like that. Then I'm going to go another 2 inches past that, and I'm going to go and pull back any sort of a ground conductor that is going to be on the outside of my cable. A lot of these have got not only just that insulation shield or semicon, but they're actually going to have a wrapped grounded conductor that goes around the outside as well. Once I've got all of that, I'm then going to follow the installation instructions. There's usually going to be some like grease and stuff like that. You're going to lube this thing up. You're going to go and pencil this. That means, cut it on an angle. So we have got, once again, a gradual entry onto these things. We do want to do the penciling as well, because it also avoids some of our corona problems that we can have. We're going to pencil that one, and then we're going to go and slide this thing all the way down to the bottom. We're going to make sure that the inside section of this section over here highlighted in green, which is going to be grounded, is going to be overlapping my actual semicon. And then there's going to be an eyelet that I'm going to go and attach at least one of my ground wires to, because that eyelet is also attached to this internal semicon that we have inside of here. Follow these things, exactly as they are rated. Over here, I've got a high K type of termination. This is going to be a class 3 termination because I see that it does not have anti-tracking, right? It's just going to go and give me stress relief and stress relief alone. Same deal, I'm going to go and use the manufacturer's guidelines. They're going to tell me how far I'm going to go and strip everything back on this cable. Once I've got everything stripped back, that's where my semicon ends, or insulation shield. This is where my dielectric ends over here. I'm going to go and take this tube and I'm going to place this tube over top. And in a lot of cases, these tubes are going to be made up of a really malleable type of rubber, but it's really tight. They're going to stretch it out over top of what looks like a plastic spring in the factory. You're going to slide this thing all the way down, and then you're going to grab the spring from the top over here, and you're just going to go and pull it out. And that spring, as it pulls out, the rubber of the high K tube, it's always really soft, is going to go and collapse in around here, and it's going to go and seal that thing off. Last of all, we're going to take a quick look over here at a class 1 or an outdoor one. This outdoor one is going to go and provide stress relief, anti-tracking, and protection against the weather. Same deal. This one is going to go and have a stress cone component. So actually, when you're doing this termination, you're going to start by doing basically this termination that we see over here. Let me just erase that over there. So you're going to start by putting on the stress cone section. Oftentimes it comes as a separate, sometimes it comes as a built-in. Put on the stress cone section. Once you put on the stress cone section, you're going to place something over top that's going to be a silicone insulation, and it's going to be very similar to my high K tube. So you're going to place this thing over top, and it's going to go all the way down over top of your stress cone. You're going to pull out that internal spring, and this thing is then going to go and collapse down over top. And then you're going to place on a third section over here, which is going to be usually a heat shrink thing that's going to go over top of the actual barrel and make the rest of your connection over top of these. Be very careful when you're making these terminations. Read everything. Make sure you understand absolutely everything. They're going to go and throw some terms at you. Penciling. Penciling is going to be where I'm going to go and take these lips, where I could go from, my insulation down, etc. I'm going to go and cut those off at an angle like that, which is then going to go and mean that anything that I shrink over top of this is going to be smooth, and there's going to be less area for trapped air. If I would place something over top of something that wasn't penciled, going to shrink like that. We're going to have an area over here. We're going to get trapped air, and that trapped air is going to go and break down. It's going to form corona inside of here, and that corona is going to go and it's a free radical. It's going to go and eat through a lot of your insulation. It's going to cause this thing to fail early. Be very careful. They give you a note over here next to mechanical damage caused by careless handling and installation methods. Poor terminations are the second biggest cause of cable failure. So usually, if there's a failure, it's because the cable got damaged during the install, but if not, it's usually then going to go and be the termination. Be careful as well when it actually comes to the connection, the high voltage connection. Make sure you remove that strand shield before you crimp this thing on, because if you leave the strand shield on there, it's not going to be as good of a connection, which means that you're going to go and develop heat, which is going to lead to breakdown inside here.